Good evening. Back to our chemistry lecture. In today's lecture, we'll continue the same thing, mole and stoichiometry. Till now, in mole and stoichiometry, we have done basic concept of chemistry, including definition of moles, moles calculations, moles and stoichiometry means application of mole in chemical reactions. And in the last class, we have just finished concept of limiting reagent and the concentration terms. In remaining two lectures, we'll do concept of equivalent mass, redox reaction, balancing of redox reactions. Before we start balancing of redox reaction, we have to revise the concept of oxidation number, oxidation state, and you have to see, to revise the meaning of reduction, oxidation, reducing agent, oxidizing agent, and then we'll balance redox reaction. So in today's lecture, the purpose is we have to revise the concept of oxidation number, oxidation state. We'll see definition of reduction, oxidation, reducing agent, oxidizing agent. And if we have time, we'll start balancing of redox reactions also, such that in the next lecture, we'll do the concept of equivalent mass. So as per oxidation number and oxidation state, the thing is concerned, is particularly irrespective of your board, it is in class 11th chapter known as redox reactions or redox as a chapter. So as per definition of, let's say, oxidation number or oxidation state is concerned, it is related to their bonding between another atoms. So oxidation number. Oxidation number, or it is oxidation state. Oxidation number or oxidation state. You can say if all polar covalent bonds of given molecule are assumed to be 100% ionic, then the charge appeared on corresponding atoms is known as their oxidation number, or you can say it is same as oxidation state also. So I'm repeating, if all polar covalent bonds of given molecule is assumed to be 100% ionic, then the charge appeared on corresponding atom is known as their oxidation number. So first thing that we have to revise that meaning of, let's say, ionic bond, covalent bond, polar covalent bond, non-polar covalent bond. For example, if it is bond between hydrogen and hydrogen, this may be another bond between, let's say, hydrogen and chlorine, and this may be another bond between, let's say, sodium and chlorine. Here, sodium and chlorine, one is highly electropositive metal and one is highly electropositive non-metal. So confirmly, the bond between sodium and chlorine is going to be, let's say, ionic bond here, with cation as Na plus and anion as Cl minus. In the case of, let's say, H2, bonded pair of electron will be exactly in middle, as both hydrogen having equal electronegativity, they are identical atoms. So no charge will appear on both hydrogen atom, and thus it is the example of, let's say, non-polar. So no pole is acquired here. So So non-polar covalent bond. Same in the case of HCl. Confirmly, chlorine is more electronegative than hydrogen. So the shared pair of electron will be more shifted towards chlorine. Hydrogen and chlorine both are non-metals, so there has to be covalent bond between hydrogen and chlorine. But as chlorine is slightly, or it is more electronegative than hydrogen, so this bonded pair of electron will be more shifted towards chlorine, due to which chlorine will be slightly electron rich and hydrogen will be electron deficient. If chlorine is slightly electron rich, it acquired partial negative charge and hydrogen acquired partial positive charge. So this partial positive charge, or you can say delta positive or delta negative, means just a partial positive charge. So partial positive or partial negative charge, it acquired pole. If it acquired pole, you can say it is the example of polar covalent bond. It is the example of, let's say, polar covalent bond. I'm repeating again, between highly electropositive metal and non-metal, it is going to be ionic bond. Between, let's say, two identical non-metal, it has to be obviously non-polar covalent bond. And between two dissimilar non-metal, for example, hydrogen and chlorine, due to electronegativity difference, bond acquire some polarity. Polarity means, it is partial positive, partial negative charge, and the bond will be polar covalent bond. As per oxidation number is concerned, let's say as per oxidation number is concerned, in the case of non-polar covalent bond, as no charge is going to be appeared on both hydrogen atom, and the oxidation number of both hydrogen atom is going to be 0 and 0 here. In the case of, let's say, HCl, hydrogen is partially electron deficient, chlorine is partially electron rich, and thus hydrogen acquired +1, chlorine can acquired -1 oxidation number. So if you imagine this bond as 100% ionic, if you imagine the bond between H and Cl to be 100% ionic, hydrogen acquired +1 and chlorine acquired -1 charge. In the case of NaCl, this bond is already ionic, containing, let's say, +1 and -1 oxidation number. So in the case of ions, whatever charge is appeared on the corresponding atom, it is its oxidation number only. But in the case of polar covalent bond, you have to assume the bond as 100% ionic. If you take more example related to this, suppose if we have molecule as CO2. CO2 consists linear structure, the same thing you have seen in chemical bonding also. Oxygen is confirmedly more electronegative than carbon and thus acquired partial negative, and carbon acquired partial positive charge. So carbon is forming 4 bonds with more electronegative oxygen. Carbon is forming 4 bonds with more electronegative oxygen, and if all 4 are assumed to be 100% ionic, then the charge appeared on the carbon should be +4. And the charge appeared on respective oxygen should be -2 and -2 each, as every oxygen is forming 2 bonds with more electropositive carbon. So in the case of CO2, carbon having +4, every oxygen acquired -2 charge each. Same in the case of, let's say, hydrogen. This may be carbon, it may be hydrogen, and let's say hydrogen. In the case of CH4, hydrogen is more electropositive than carbon, so acquired partial positive, and let's say partial positive charge, and carbon should acquired partial negative charge. So as every hydrogen forming 1 bond each with more electronegative carbon and should acquired, let's say, +1 oxidation number each, if every bond of carbon is assumed to be 100% ionic, then the oxidation number of central carbon should be -4. So my point is, let's say in the case of ionic bond, whatever charges appeared on corresponding atom, its oxidation number only. But in the case of polar covalent bond, you have to assume that bond as 100% ionic, and then you have to see the charge appeared on corresponding atom there. I hope you understand the definition of oxidation number or oxidation state. We'll see a few rules related to oxidation number or oxidation state, how to find out oxidation number. But basic thing is, in the case of ions, whatever charges appeared is oxidation number. And in the case of polar covalent bond, you can assume it as 100% ionic. Let's move to the next thing is, one is you have to see electronegativity order. Electronegativity order of different element. Here, fluorine is found to be most electronegative element, then it is oxygen, then nitrogen and chlorine having nearly same electronegativity. Somewhere they are more electronegative than carbon. Carbon is somewhere more electronegative than hydrogen. Hydrogen may be more electronegative than any of the electropositive metals. So fluorine is most electronegative element. Oxygen, you can assume, is second most electronegative element. Nitrogen and chlorine having nearly same electronegativity. They are found to be more electronegative than, let's say, carbon. Carbon is found to be more electronegative than hydrogen. So if you remember something related to, let's say, electronegativity as Pauling scale, the same thing you have seen somewhere in, let's say, periodic properties chapter. Here, electronegativity of sodium is found to be 0.7 on Pauling scale. Hydrogen is found to be 2.1. Carbon is found to be 2.4. Both nitrogen and chlorine having 3.0 each. Oxygen is found to be 3.5 and fluorine is found to be, let's say, 4.0. It is based on Pauling scale, or even without scale, you can simply say there is no need to remember their values. So fluorine is found to be more electronegative than oxygen, nitrogen, and chlorine, carbon, hydrogen, sodium. Same if we have directly, suppose compound as FeSO4. The compound is ferrous sulfate. The compound is ferrous sulfate. And how we know it is ferrous sulfate? Since if you see in the case of sulfate, we have -2 charge here. So iron has to be +2. It is in, let's say, 1:1 charge ratio of cation and anion. So one is ferrous sulfate, it is Fe2 plus, and sulfate ion having a carry 1:1 ratio. So ferrous sulfate, or sometime in your books it may be written as iron 2 sulfate. So as per +2 is concerned, +2 is oxidation number of iron. Oxidation number of iron. And sometimes usually which is written in Romans, this 2, it is their oxidation state. Otherwise, conceptually, you can say oxidation number and oxidation state is going to the same thing. It is 2, +2 for iron here. Before we do some complex example related to oxidation number calculation, you can see few rules related to oxidation numbers. So rules to find out complex oxidation number. Rules to, find out complex oxidation number. First rule is, oxidation number of any atom in its elemental state. In its elemental state is, it is 0. Oxidation number of any atom in its elemental state is 0. For example, somewhere if it is written as, let's say, sodium, it may be, suppose, Cl2, it may be O3 ozone, it may be P4 phosphorus, it may be sulfur, it may be, let's say, B12 for boron, it may be, let's say, for diamond, etc. So all these are found to be element only. So oxidation number of sodium, when it is written as Na only in elemental state, is found to be 0. Cl2 chlorine oxidation number will be 0, ozone oxidation number 0, phosphorus oxidation number 0, sulfur having 0 oxidation number, boron having 0 oxidation number, even diamond, carbon having 0 oxidation number. So any atom in its elemental state, oxidation number is found to be 0 here. Similarly, second rule is oxidation number. Oxidation number of hydrogen. Oxidation number of hydrogen is found to be -1, 0, or is found to be -1, 0, or +1 only. For example, if hydrogen combine with itself, hydrogen may combine with more electronegative element and hydrogen may combine with more electropositive element. Now, since its valency is found to be 1 only, so it can combine with itself more electronegative element or more electropositive element. Hydrogen oxidation number in H2 is found to be 0. In HCl, it is going to be +1 as combined with more electronegative element chlorine. And in the case of hydrogen, it is found to be -1 combined with more electropositive sodium here. Similarly, oxidation number. Oxidation number of oxidation number of alkali metal. Oxidation number of alkali metals is found to be 0 and +1 only. For example, if it is written as sodium Na, or it is written as, let's say, suppose Na2O. In the case of sodium, oxidation number is found to be 0, and in the case of Na2O, oxidation number is found to be, let's say, +1. So oxidation number of any atom in its elemental state is 0. Oxidation number of hydrogen is found to be, let's say, -1, 0, or +1 only. Oxidation number of alkali metal is found to be 0 or +1 only. Next, fourth rule is oxidation number of alkaline earth metal. Again, I hope you know alkaline earth metal is metal of, let's say, group 2 of periodic table, including, let's say, you can say it is beryllium, it is magnesium, it is calcium, it is strontium, barium, radium. So oxidation number of alkaline earth metal can be either 0 or plus 2 only. For example, if it is written as magnesium, or let's say it is MgCl2. In this case, oxidation number of magnesium is 0. In this case, oxidation number of magnesium is found to be, let's say, plus 2. So in any of the combined state, oxidation number of magnesium is going to be plus 2. And in free state, in elemental form, oxidation number of any element including magnesium has to be 0. Next one. Oxidation number of fluorine. Oxidation number of fluorine is either 0 or -1 only. Fluorine is found to be most electronegative element, so in combined state it can't be positive oxidation number. So it can be either 0 or -1 oxidation number. For example, if it is written as F2 only in fluorine combined with fluorine, or it is elemental form of fluorine, or it may be, let's say, sodium fluoride. Oxidation number of fluorine is 0 here, and oxidation number of fluorine is going to be -1 here. Same. Just remember this statement. This statement is, not applicable for other halogens. This statement is not applicable for other halogens. Halogens means elements of, let's say, group 17th, including fluorine, chlorine, bromine, iodine. For example, in the case of other halogens, compounds may be, let's say, ClF3 compound may be, let's say, IF7. So here oxidation number of fluorine is going to be -1 each. But if you see in the case of chlorine, its oxidation number is found to be, let's say, +3. It is forming 3 bonds with more electronegative fluorine. So it is +3. Same in the case of iodine, it is going to be +7. Next one. Oxidation number. Oxidation number of oxygen is, -2, it is -1, it may be -half, it may be 0, it may be +1, or it is +2. So oxygen can have different type of oxidation number, including -2, -1, -half. It is 0, +1, and +2. So whenever oxygen having -2 oxidation number, it may be represented as O2 minus, and this ion is known as oxide ion. This ion is known as oxide ion. For example, if we have, let's say, CO2, if we have SO2, if we have SO3, if we have, let's say, suppose Na2O, if we have, let's say, CaO, if we have, let's say, P4O10, if we have, let's say, anything, suppose if we have MgO, all these compounds are oxides. So oxidation number of oxygen in every of these compounds is found to be -2. Same, oxidation number of oxygen can be -1. In -1, oxygen may be represented as O22 minus, and this ion is known as, we know, peroxide ion. For example, if it is, let's say, H2O2, this may be, let's say, Na2O2, this may be, let's say, BaO2. So in which oxygen oxidation number is found to be, let's say, -1. It may be, let's say, -half as a oxidation number. In this case, oxygen may be represented as O2 -1. And similar to oxide and peroxide, this ion is known as superoxide ion. For example, let's say it is KO2. So KO2 as a compound is concerned, it is known as, let's say, potassium superoxide. Oxygen can have zero oxidation number also. So for zero oxidation number, you can say either it may be O2 or O3, which is elemental state of oxygen, or the compound may be of this type also, HOF, in which fluorine having -1 by rule, hydrogen can have +1, and thus oxidation number of oxygen should be, let's say, 0 here. Oxygen can have positive oxidation number only with fluorine, as only fluorine is found to be, more electronegative than oxygen. So in the case of O2F2, oxygen is found to be +1, and in the case of OF2, oxygen is found to be, +2 oxidation number. So as per oxidation number of oxygen is concerned, it can be +1, it can be +2 also. Now, can you suggest me what is the most common oxidation number of oxygen out of -2, -1, -half, 0, +1, and +2? So most common oxidation number. Most common oxidation number of oxygen is, most common oxidation number of oxygen is -2. So usually in all oxides, through oxide we'll have oxy acid and base. So we have oxide base salts. In all these cases, oxidation number of oxygen is going to be, let's say, -2. So I'm repeating again, through these oxides, we have formation of, let's say, corresponding acid, let's say H2SO4, acid may be H2CO3, the base may be, let's say, calcium hydroxide, base may be, let's say, magnesium hydroxide, base may be, let's say, NaOH here, corresponding salt may be CaSO4, this may be, let's say, Na2CO3, this may be, let's say, magnesium phosphate. So magnesium phosphate formula may be Mg3PO4 whole twice. In all these acid, base, and salt, oxidation number of oxygen is going to be -2. I hope you note down this thing. Next is, maximum possible. Maximum possible oxidation number of any element. The maximum possible oxidation number of any element equal to, plus of its valence electron, and similarly minimum oxidation number of any element is, minus of 8 minus valence electron. So maximum possible oxidation number of any element equal to plus of valence electron, and similarly minimum oxidation number of any element equal to minus of 8 minus valence electron. For example, in the case of nitrogen, which atomic number is found to be 7, it is 2,5 is oxidation, electronic configuration, and 2,5 as electronic configuration. The minimum oxidation number of nitrogen is going to be -3, and maximum oxidation number of nitrogen is going to be +5. Similarly, in the case of sulfur, it is 2,8,6, in which minimum oxidation number is -2 and maximum oxidation number is found to be +6. So nitrogen can vary from -3 to +5. Sulfur can vary from, let's say, -2 to +6. Same, suppose if we have chlorine 17, its electronic configuration is 2,8,7. So its minimum oxidation number may be -1, and its maximum oxidation number is going to be +7. Oh, we'll see some example related to this, related to oxidation numbers. So one more rule related to calculation of oxidation number. Let's say next rule is the algebraic sum algebraic sum of oxidation numbers. Algebraic sum of oxidation numbers of all atoms. Algebraic sum of oxidation number of all atoms of given element. Algebraic sum of oxidation numbers of all atoms of given element is resultant charge appeared on molecule and ion. Algebraic sum of oxidation number of all atoms of a given element is resultant charge appeared on molecule or ion. For example, suppose if we have any compound as, let's say, KMnO4, potassium permanganate. So usually we know oxidation number of potassium here, oxidation number of manganese, and oxidation number of oxygen in general. So potassium is alkali metal, its oxidation number has to be +1. Oxygen is alkaline, oxygen oxidation number is usually, let's say, it is -2. And if we do not know oxidation number of manganese, it can assume to be, let's say, X here. The resultant charge on this molecule is 0. It is neutral molecule. So oxidation number should be, let's say, potassium is +1, manganese is going to be X, oxygen in total it is 4 times of -2, and the resultant charge is 0. This X has to be equal to +7. X has to be, let's say, +7 here. Same if we have, let's say, dichromate ion. In dichromate ion, oxygen oxidation number, usually we know it is going to be -2. Chromium oxidation number, you can imagine it as X. The resultant charge on dichromate ion is, let's say, -2. So again, the algebraic sum means you can imagine twice of X for chromium. It is 7 times of -2 for oxygen, and the resultant charge is found to be, let's say, -2. From here, the value of X comes out to be, let's say, +6. Similarly, let's say suppose ion is going to be N2H5 plus. It is known as hydrazinium ion, in which hydrogen, which is found to be more electropositive than nitrogen, can have +1 by rule. You can imagine, let's say, nitrogen is going to be X. The resultant charge on this hydrazinium ion is found to be, let's say, +1. So it is twice of, let's say, X plus 5 times of +1 should be its resultant charge as +1, and the value of X is going to be, let's say, -2. So as per oxidation number of nitrogen is going to be -2 here. Oxidation number of chromium is going to be +6. Oxidation number of manganese in KMnO4 is found to be, let's say, +7. So it is just to find out how we find out oxidation number here. We'll do just 2 questions related to calculation of oxidation number, and then we'll see definition of reduction, oxidation, oxidizing agent, reducing agent. I hope you note down this thing. Next is, so let's say first question related for today's lecture is find out oxidation number. Find out oxidation number of nitrogen in following compounds. find out oxidation number of nitrogen in following compounds. So as per compounds are concerned, these compounds may be, let's say, ammonium ion. This compound may be, let's say, N2H4. This compound may be, let's say, NH2OH. This compound is N2. Compound may be N2O. Compound may be NO. Compound may be NO2 minus. Compound may be NO2. Or let's say I will start from starting only. You can write all these compounds in more compressed manner. So it is ammonium ion. This compound is going to be N2H4. This compound is, let's say, NH2OH. This compound is N2. This compound is N2O, which is nitrous oxide. This compound is NO. Another compound is going to be, let's say, NO2 minus. This may be, let's say, NO2. And another compound is, let's say, HNO3. So you have to find out oxidation number of nitrogen here. You can apply any logic here. Yes, in first one, if you have to do calculation from scratch only, you can imagine nitrogen is going to be X, hydrogen is going to be +1. So it is X plus, 4 times of +1 should be resultant charge as +1, and thus X value should be -3. Similarly, if you do all these calculations, second is found to be -2, third is going to be -1. N2 oxidation number is 0. N2O it is found to be +1. NO it is found to be +2. In the case of NO2 minus, it is +3. In the case of NO2, it is going to be +4. And in the case of HNO3, oxidation number is found to be, let's say, +5. So here nitrogen vary from -3 to +5 as a oxidation number. So in this case, oxidation number of nitrogen vary from, let's say, -3 to +5. So we know nitrogen, as per nitrogen is concerned, its electronic configuration was 2,5. So its minimum oxidation number is going to be -3, and its maximum oxidation number is going to be +5. We have just seen some rules related to minimum and oxidation number. And in these examples, if you see, nitrogen oxidation number vary from -3 to +5. I hope it is clear related to oxidation numbers. Next thing is, let's do question number 2. Find out oxidation number of, underlined element in let's say following compound. You have to find out oxidation number of underlined element in following compound. You have to find out oxidation number of underlined element in following compounds. Few examples of this underlined element may be, suppose if it is, PbO2, it is KO2, it is BaO2, it may be, let's say, PV3O4. So you have to find out oxidation number of lead, potassium, barium, and lead, let's say. Now, suppose the another compound may be CrO5. It is very common compound. Here, oxidation number you have to find out for, let's say, chromium. Same. If another common compound is, let's say, H2S2O8, you have to find out oxidation number of sulfur. If we have to find out, let's say, oxidation number of Fe and CO. Fe and CO, it is, iron carbonyl. And let's say if we have to find out oxidation number of nitrogen in N3H, where it is hydrazoic acid, N3H. PbO2 is concerned, lead is found to be in the same group as we have carbon. So similar to, let's say, CO2 as carbon dioxide, PbO2 is known as lead dioxide, and oxidation number of lead is going to be, let's say, +4 here, as every oxygen oxidation number is -2. In the case of KO2, potassium, we know by rule it is alkali metal. Its oxidation number has to be just +1, as superoxide ion O2 consists -1 charge. In the case of BaO2, barium oxidation number is going to be, let's say, +2, as every oxygen having oxidation number is -1 here. In the case of PV3O4, the oxidation number of lead is going to be, let's say, +8/3. It is on an average oxidation number. As far as CrO5 is concerned, if we assume every oxygen as -2, then the chromium oxidation number is going to be +10, which is impossible. Maximum oxidation number of any element can be just +8. So in the case of CrO5, if you see its structure, CrO5, it is going to be this. It is oxygen and this. It is also known as butterfly shape. Oxidation number of central chromium has to be +6 here, as chromium is forming 6 bonds with more electronegative oxygen. Same in the case of H2S2O8. The structure is also, let's say, oxygen, oxygen, and double bond O, and OH here. The oxidation number of sulfur is going to be +6 here, as sulfur is forming, 6 bonds with more electronegative oxygen here. In the case of FeCO5, as per CO is concerned, it is carbon monoxide, it is neutral, and the oxidation number of iron is found to be, 0 here. Same in the case of N3H, oxidation number of hydrogen is going to be +1. And as per oxidation number of nitrogen is concerned, nitrogen oxidation number is going to be, let's say, -1/3 on an average. So till now, this was just the revision of oxidation numbers. So we have just seen the definition of oxidation number. We have seen few rules how we can find out oxidation number, and we have seen, let's say, how effectively, let's say, with the help of their structures or the algebraic formula rule, we can find out their oxidation numbers also. Now let's say see the definition of reduction and oxidation. Reduction means, reduction is, reduction or decrease in oxidation number. Reduction is reduction or decrease in oxidation number due to, gain of electron. So reduction or decrease in oxidation number due to gain of electron is known as reduction. You can simply say it is let's say addition of oxygen or removal of, so it is reduction means addition of hydrogen. So it is addition of, hydrogen or removal of oxygen. Reduction or decrease in oxidation number. It is, gain of electron. It is addition of hydrogen or it is removal of oxygen. Okay. Next thing is, for example, if it is, permanganate ion is going to reduced into, let's say, Mn2 plus. So as per oxidation number of manganese is concerned, it is +7, and here it is found to be +2. So we have to have addition of, let's say, 5 electron here, such that manganese from +7 oxidation number decreases to +2 oxidation number. Same in the case of, let's say, dichromate ion. Dichromate ion gain few electron and it can convert into 2 chromium 3 plus. So here oxidation number of chromium is +7, wahan +3. So it is +6, sorry. As per chromium oxidation number, it is going to be +6. From +6, it is +3. So per chromium, it will gain 3 electron, and per 2 chromium atom, it will gain 6 electrons here. Same if you see simple reaction including Cl2. Cl2 will gain 2 electron and it will convert into 2 chloride ion. Here oxidation number of chlorine is 0 and it is found to be -1. So for every 1 chlorine atom, 1 electron will get transferred. And for 2 chlorine atom, you can simply imagine 2 electron will transfer. Same, let's say it is, V2O5 vanadium pentaoxide will gain few electron and it will convert into 2 vanadium. Here oxidation number of vanadium is going to be +5. Here oxidation number is 0. So if we add, let's say, 10 electron in total, so total oxidation number of 2 vanadium on reactant side is +10. Product may it is found to be 0. So you have to add 10 electron with V2O5 such that it will convert into 2 vanadium. So overall, all these reactions are known as, let's say, reduction reactions. I hope it's clear. Permanganate ion will gain few electron, dichromate ion will gain few electron, Cl2 will gain few electron, vanadium pentaoxide will gain few electron. Now, apart from reduction reaction, next thing is, let's say, oxidation. Oxidation. Oxidation means it is increase in oxidation number by losing electron. It is a gain of electron, or sorry, it is addition. It is addition of oxygen, or it is removal of hydrogen. For example, let's say if it is sodium is converting to Na plus while losing electron, it is ferrous ion is converting to ferric ion by losing electron. It may be, let's say, zinc is converting to ZnO by losing 2 electron. Here, oxidation number of sodium is 0. It is going to be +1. Here it is +2. It will be +3. Here it is 0, and it is going to be +2. So it is increase in oxidation number due to loss of electron. Similarly, suppose if it is NH3 is converting to N2, so 2 mole of nitrogen. Here oxidation number of nitrogen is -3. It is going to be 0 here. And it has to lose, let's say, 6 electrons here. So all these reactions are example of, let's say, oxidations. All these reactions are example of oxidation. I hope you understand the definition of reduction, definition of oxidation here. So further, apart from reduction and oxidation, next definition is going to be, let's say, redox. Redox reaction. In the case of, let's say, redox reaction, you can say simultaneously reduction and oxidation. Simultaneously reduction and oxidation is known as, let's say, redox reaction. Simultaneously reduction and oxidation is known as redox reaction. For example, suppose if we have Cl2 will gain 2 electron and it will convert into 2 chloride ion. This reaction is going to be, let's say, reduction. It is a reduction, decrease in oxidation number of chlorine. Same, let's say it is 2Na converting to 2Na plus 2 electron. And this reaction, we know it is known as oxidation. So we have reduction and oxidation, and if we add both half, reduction as well as oxidation, here it is 0 oxidation number decreases to -1. Here it is 0 oxidation number increases to, let's say, +1. If we add both reactions, you will get 2Na plus, it is Cl2 will give, let's say, 2Na plus Cl minus, in which oxidation number of sodium increases from 0 to +1, and for chlorine it decreases from 0 to -1. So from here it is Red, and from here you can choose as OX, and this complete reaction is known as, let's say, redox reaction, in which we have reduction as well as oxidation. Apart from, let's say, redox reaction, this sodium is known as reducing agent here. It is known as reducing agent as per Cl2 is concerned. It is known as oxidizing agent. So as per reducing agent is concerned, it get oxidize itself to reduce other, and as per oxidizing agent is concerned, it get reduce itself to oxidize other. So I'm repeating, whenever we have simultaneously reduction as well as oxidation, complete reaction is known as redox reaction. For example, in this case, Cl2 get reduced and sodium get oxidized. In this case, sodium is reducing agent, Cl2 is oxidizing agent. And in total, you can say it is redox reaction. Apart from definition of, let's say, redox reaction, next thing is you can see a few more example of another type of redox reaction known as, let's say, disproportionation. It is disproportionate reaction. The meaning of disproportionate reaction is the redox reaction in which same element get reduced as well as oxidize. The redox reaction in which same element get reduced as well as oxidize is known as disproportionate reaction. Is known as disproportionate reaction. For example, let's say if it is Cu2O on heating Cu2O, it will convert into Cu and let's say CuO, in which oxidation number of copper is +1. It decreases to 0 and simultaneously increases to +2. So copper get reduced as well as oxidize here. So it is typical example of disproportionate reaction. Same, let's say if it is Br2 in balance reaction, you can say let's say it is 6KOH. It will give KBrO3. It gives 5KBr plus H2O. Here oxidation number of bromine is 0. Increases 2 plus 5, decreases to -1. So in the reaction, same element bromine get oxidized as well as reduced. So it is a typical example of, let's say, disproportionate reaction in which same element bromine get oxidized as well as reduced. You can take more example related to this is, let's say it is H2O2. H2O2 can decompose to give, H2O and half O2, in which same element oxygen is going to be reduced as well as oxidized. So they are typical example of, let's say, disproportionate reaction. I hope clearly you have noted down this. Disproportionate reaction. Now the next topic is going to be balancing of these redox reactions. Balancing of redox reaction, in which, let's say, first reaction you can imagine, it is zinc when treated with V2O5, it will give vanadium and let's say zinc oxide. So obviously it is going to be, redox reaction in which zinc is 0, increases up to +2, and vanadium is +5, decreases up to 0 oxidation number here. So in which zinc get oxidized from 0 to +2, and vanadium pentaoxide in which vanadium get reduced from +5 to 0 oxidation number. As for simple balancing is concerned, you can do balancing of atom, whatever reactant we have, whatever atoms we have for oxygen on the reactant side, we have same on the product side also. So if you multiply zinc oxide by 5, oxygen atom will be balanced, and if you multiplied by this 2, vanadium atom can be balanced, and if you multiplied it by 5, let's say zinc atom is also balanced. So it is balanced redox reaction. But suppose if we have, let's say, another reaction as it is I2 when treated with ozone, it can convert into, let's say, I4O9 and O2. It is also a redox reaction in which iodine get oxidized. So, iodine is going to be, let's say, reducing agent here and ozone will be, let's say, oxidizing agent here. So I2 plus ozone, it will give I4O9 and it will give, let's say, O2. As per balance reaction is concerned, we can do many type of balancing here. For example, it is plus 2I2. It will give, let's say, 9O3. It will convert into I4O9 plus 9O2. It is one of the balancing, you can say. It is one of the balancing. Same, another balancing may be, let's say it is 2I2 plus, let's say it is 8O3 is converting to, I4O9 and oxygen atoms remaining. So 8 3s are 24, 24 minus 9, it is 15. So you can simply say it is 15Y2O2. Another balancing of reaction maybe it is, let's say 2I2 plus, it is 7O3 will convert into I4O9. 21 minus 9 is 12. So you can say it is 6O2. Another balancing of reaction may be, let's say 2I2 plus, 5O3. It will convert into I4O9. Out of 15, if we subtract 9, it is 6. So you can say it is 3O2 remaining, and so on, and so on, and so on. So there are the many balancing possible. Out of this, only this one is correct, and remaining are wrong. So Pandits, we have to have some significance of, balancing of redox reaction. It is not simply atoms balancing. In redox reaction, apart from balancing of atom, you have to balance balance their charge. You have to balance their oxidation number. You have to balance loss of electron, gain of electron. So overall, we have to understand few methods to balance the reaction. So if we revise for today's lecture, in today's lecture, we have see definition of oxidation numbers. Then we'll see the method to find out oxidation number, rules for oxidation numbers. And then eventually we'll see definition of reduction, oxidation. In the next class, we'll see balancing of redox reactions also. So till now, till that lecture, you can just revise the definition of oxidation number, how do we find out oxidation number. Since in the next lecture, we are going to use calculation related to oxidation number. So you have to do fast calculation for oxidation number to balance the redox reaction. So in next lecture, we'll see balancing of redox reaction as well as concept of equivalent mass. And the next lecture is going to be your last lecture for mole and stoichiometry. So keep revising your notes, do practice for calculation of oxidation number. And in the next class, we are going to do, balancing of redox reaction. So that's all from my side for today's lecture. Yeah, good day.